The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. Welcome and thank you for attending this morning's webinar, A Practical Methodology to Apply API 1163 ILI Systems Qualification Standard. I'm Marissa Davis and I'll be facilitating. So let's try this again, shall we? For those of you who weren't here with us last week, Bernardo was scheduled to present on this topic last Tuesday, but about as soon as it got started, we had some technical difficulties with his audio. We had to pull it and reschedule it for this morning. And for those of you that were with us, welcome back, and thank you so much for your patience and understanding. We will have some time left at the end of the webinar for questions. So if you have some, make sure you send them using the question function and Bernardo will be happy to get to them. So let's get started. The host of today's webinar, G2 Integrated Solutions, provides responsive support and a comprehensive suite of asset integrity, engineering, GIS, field services, regulatory, and technology solutions that address asset performance through its lifecycle. For more details on our services, please visit our website. All right, presenting this morning, we have G2's Principal Integrity Consultant, Bernardo Cuervo. Bernardo has 30+ years of experience in pipeline design, construction, and ILI. He is a master trainer of the National Center for Construction, Education, and Research. He's co-chair of the Corrosion Control course at the University of Oklahoma, and he is a PHMSA associate instructor for the safety evaluation of inline inspection programs. So with that, Bernardo, I'll let you take it from here.
Thank you, Marisa. Today we're going to talk about some of the changes in gas pipeline safety regulations. PHMSA will increase the requirements of Section 192-150, passage of internal inspection devices, and will incorporate 3 documents by referencing the new Section 192-493, inline inspection of pipelines. Finally, we'll go over a clear example of a specific implementation for a pipeline operator so that you can see what you need to do to be in compliance. So let's get started. But first, let me take you back in time 55 years to the year 1965. It is March 4, 6:03 a.m. A big explosion is about to happen. Natchitoches, Louisiana, a high-pressure natural gas pipeline manufactured shortly after 1945 exploded, and the flames from the escaping gas were about 400 feet high before workers managed to stop the flow of gas by hand. The explosion created a crater 75 feet long by 30 feet wide. 3 sections of pipe with a total weight of 1,000 pounds were ejected as far as 350 feet away. 5 houses across the Natchitoches Country Club on Highway 1 were destroyed in the blast and fire. State police estimated the damage from the blast at over $1 million, dollars of 1965. 17 people were killed, including 9 children. Several families escaped from nearby homes, including 9 people who were severely burned. 6 cars and 3 trucks were destroyed. Some of them were completely melted by the intense heat of the fire. The fire cremated an area of almost 14 acres. There had been other pipeline incidents before, but this explosion focused the attention of pipeline safety and led to then-President Lyndon Johnson to call for the formation of a National Pipeline Safety Agency, which eventually would be created 3 years later in 1968. 10 years earlier, the same pipeline had ruptured once about 300 yards away in the spring of 1954. And this brings us to the moral of the story. And the moral of the story is best expressed by George Santayana's famous quote, "Those who fail to learn from the history of the are doomed to repeat it." But let me take the liberty to change his words. Those who fail to learn from pipeline history are doomed to repeat it. Hopefully by the end of this presentation, the words of George Santayana will make more sense. Pecos River, New Mexico, Saturday, August 19, 2000. A 30-inch diameter natural gas transmission pipeline ruptured and exploded, reaching a temperature of 1200 degrees Fahrenheit. The fireball, 500 feet tall, was visible 20 miles away in Carlsbad, New Mexico. Before the firemen could get close, they had to retreat and wait for workers to turn off the flow of gas by hand. A family of 12 was caught in the fireball. 5 of them were young children. They were camping beneath this bridge. Only one victim would survive past the first few days. The force of the explosion created this crater, 113 feet long by 51 feet wide, 113 feet long by 51 feet wide. And the distance between the rupture site and the east bank of the river where the family was camped was almost 700 feet. A 49-foot section of the pipe was ejected, and part of it was found almost 300 feet away. The pipeline was laid in 1950, and in all that time, it had never been checked on the inside. Let's fast forward 10 years to 2010. In San Bruno, California, a 30-inch diameter segment of an interstate natural gas transmission pipeline ruptured in a residential area. Approximately a total of 48 million cubic feet of natural gas ignited. It took 95 minutes to stop the flow of gas. That was a very long night. This is not a scene taken from a dystopian movie. The flames damaged 70 homes and completely destroyed 38. 8 people were killed, 58 were severely injured. The rupture produced a crater about 72 feet long by 26 feet wide. A 28-foot-long section of pipe that ruptured with a total weight of about 3,000 pounds was found 100 feet south of the crater. In 1956, the 30-inch diameter pipe, grade X52, with a wall thickness of 375 thousandths of an inch, installed with a substandard and poorly welded section that was even visible the flaw, over time grew to a critical size, causing the pipeline to rupture during a pressure increase. So our future cannot be more of this. These pipelines have never been picked, so a good place to start is to look at the recent changes to our current safety regulations. Our current pipeline safety regulations in Section 150 require that pipelines be designed and constructed to accommodate ILI devices. But up to this point, they were silent on technical standards for implementing requirements to assure they were designed and built for inline inspection assessments. The strengthening of Section 150 by incorporating NACE Standard Practice 0102 will establish consistent standards for the design and construction of piggable pipelines. But it is not enough to internally inspect the pipeline. You need to do it the right way. For this reason, the gas mega rule also includes this new section 192.493. It means that when conducting inline inspections of gas pipelines, you must comply with the requirements and recommendations of 3 documents. Let's review these documents. The first one, the NACE Standard Practice 0102, in Section 7, New Construction Planning for Inline Inspection Surveys, will establish technical standards for the design and construction of pipelines to accommodate inline inspection devices. It will also improve inline inspection tool selection. The second document The API Standard 1163 Inline Inspection Systems Qualification Standard is an umbrella document that covers all aspects of inline inspection from the planning to the verification and validation of the inline inspection run. And finally, the third document, the ANSI AS&T ILI PQ Inline Inspection Personnel Qualification and Certification, will promote a higher level of safety by establishing consistent standards to qualify the people behind your inline inspection. Operators need to verify the competence of the inline inspection personnel, their education, their training, their experience and skills. But it is more than just requesting a piece of paper from the ILI vendor with just a certification. There is much more to audit: written procedures, training programs, examinations, testing of personnel, and performance evaluations. These new gas requirements will be effective on July 1st, 2020, in just a couple of weeks. So what is the problem? Previously, the acceptance of an inline inspection run had been based primarily on a validation process where the results of the inspection were compared to the results of field measurements. At best, the comparison can only show that the inline inspection run is consistent or inconsistent with results collected in the field. The procedure does not prove that the inline inspection meets its performance specification. The inline inspection run is accepted unless evidence to the contrary is found once the verification program has been finished, sometimes many months after the launching of the inline inspection tool, when it may be too late. So the solution: we need a systematic approach to clearly evaluate the quality at each step of the inline inspection run, not just at the field verification process, and decide based on that systematic approach whether the run should be accepted or rejected at any stage of the process. The new process is this 11-step process, and is divided to ensure that the procedures are followed during all the way of the inline inspection. So prior to the run, during the run, and after the inspection. The fundamental premise of the methodology is that high-quality inline inspection data is a consequence of technology, planning, and execution. Let's review the first step, the pre-run stage, and then with the first checkpoint, the tool selection. After the basic information has been input, the operator needs to assign a score to each item to make sure that the particular procedure is followed. For example, you need to make sure that during the selection process, the main threat and possible combination of threats have been identified. Then the target anomalies must be reviewed, and so on. All checks must have a pass or a conditional pass for the run to be accepted. A score pass indicates that the proper procedure was followed. A conditional pass indicates that some irregularities were found in the procedure, but that the effect on the data is not significant, or that additional actions may be required to ensure that the conditional pass is resolved. Finally, a fail will show that you cannot continue unless you are going to accept a compromise in the data. The final cumulative check is a review of all the conditional passes to ensure that the overall effect on the data is acceptable. Fail in this case indicates that the data will be compromised in some way and that the run cannot be accepted. So let's complete the procedure to eliminate the fail score so that we can proceed. There is a lot of inline inspection tools available, but which tool gives you the biggest bang for the buck? The NACE standard Practice 0102 provides this table with anomaly types and available tool categories, indicating their fit for the objective of the inspection. However, the selection of the inline inspection tool must be completed with documentations like the APA Recommended Practice 1160, Managing System Integrity for Hazardous Liquid Pipelines, which provides a process for assessment of potential risks, and the ASME B318S, Managing System Integrity for Gas Pipelines, which provides information necessary to develop and implement an effective integrity management program. An electronic version of the table is included in the checklist. There is no best tool, no silver bullet. There is, however, a best tool for specific inspection requirements, but you need to have a clear understanding of limitations and advantages of each inline inspection technology. To understand, you need to understand the type of anomalies that you are looking for, as well as the pipeline operating parameters. To select the best tool for the job is not an easy task, as you can imagine, and must be done carefully. The second step is the system performance, and this will assess the performance of the selected inline inspection tool to ensure not only that the technology can detect and size the anomalies, but also that the inspection system is able to deliver quality data, as demonstrated by its history of successful runs. In some cases, you may decide to run an untested technology, but this will require an ample and extensive validation before using the run results to assess the threats of your system. In a similar manner, if you have not previously used a particular tool, you will need to request an inline inspection vendor with relevant documentation demonstrating the successful performance of that particular inline inspection tool or technology that you want to use. The third one is the planning. Now that you have verified the historical system performance of the tool, it is time for the planning. And one of the most important steps during planning is the cleaning activities. Cleaning targets must be met prior to the inspection to avoid degradation of the data quality or even complete loss of data. Some technologies are more susceptible to debris, wax, and dirt than others. But in general, you want to clean for inspection. Adequate planning and preparation makes a difference between a successful run and a failed run. Any short radius bands should be addressed on a case-by-case basis. Bands installed in a back-to-back configuration that is without a section of a straight pipe between the bands can present a sticking hazard for inline inspection tools. Field bands and river crossings must be reviewed throughout the survey because they become a hazard also, especially in older construction. They may contain tight radius bands, even miter bands, barred and back-to-back tees, branch connections. 30% of the pipe diameter or greater should have scraper bars. Valves. Reduced pore valves can result in tool damage, and the list goes on and on. A complete pipeline questionnaire is part of the inline inspection planning. So it is important to provide as much information as possible to the vendor to avoid unforeseen problems and delays. Here is where the questionnaire comes handy. For example, wall thickness is an important parameter for which some tools need to be calibrated, and therefore there must be considered. So in addition, the ILI vendors needs to consider changes in wall thickness that are less than 1/4 of an inch or greater than 1/2 an inch. For a smaller diameter, lined with heavy wall pipe may severely limit the types of tools that can be successfully used. The next step is the pre-run preparation. These checks are used to ensure that the inline inspection tool is in good working condition. Will the tool the mechanical and electronic components of the tool perform as designed. There are two types of checks to resolve this question: mechanical checks and function checks. Here is a field technician performing mechanical checks on a 56-inch MFL tool near the 1980s. Mechanical checks are used to confirm the mechanical integrity of the tool prior to the run. The other type of checks are the function checks. They confirm the functional integrity of the tool prior to loading the inline inspection tool into the launcher. In general, these checks are somewhat specific to each technology and vendor. For this reason, the function checklist must be provided by your ILI vendor well in advance to the inspection to complement your pre-checklist. Some examples of pre-run function checks are all components of the inspection tool must be properly initialized, confirm the availability of power supply, confirmation that all sensors are operational, confirm availability of data storage, etc. Mechanical checks in the field are mostly visual and specific to each technology too. In the same manner as with the functional checklist, the pre-run mechanical checklist must be provided by the ILI vendor to complement this checklist. Some examples of mechanical checks are a general visual inspection of the tool, confirming that the pressure seals around electronic components are adequate, verify the integrity of cups, make sure that all wheels are intact and moving correctly. And usually photographs will be attached to the checklist to verify the actual conditions of the tool before putting it in the launcher. Run execution. Here is where the fun part begins, but it's no time to take a break and wait. There are a lot of things to do. Is the actual inspection being conducted in a way that ensures high quality data? Is following established standards? A job-specific plan that includes technical requirements, responsibility, emergency contacts, procedures, work site preparations, and mobilization is important. Here also some of the activities that need to be performed during the run execution phase. Check that the tool is run as per the planned picking procedure. Check that the requirements for handling and placing the inline inspection tool into the launch barrel are defined. Check that the line conditions for the tool launch are as expected, and that the launch proceeds as planned. Check the fluid composition of your pipeline, the flow rate, temperature, and pressure, that they must be in accordance with the planned procedure. Check that the tracking of the tool is in accordance to the plan. Reference locations for above ground markers, AGMs, must be enough to meet the location accuracy stated in the performance specification. The actual location of each AGM must be measured and documented. The service provider of your inline inspection or the service provider of your AGMs must set the appropriate tool detection threshold on the AGMs to guarantee the proper detection of the boxes. After the run execution, the post-run checks comes again. You trap the tool in one piece, but now there is no time to celebrate like Bob here. You cannot celebrate your small win, not yet. It is time for more functional and mechanical checks. So it's time to get your hands dirty. It's time to make mechanical checks. So in the same way that with the pre-run checks, you have to perform a set of mechanical and functional checks. And examples of them, some are general visual inspection. But now you have to look for damage that may occur during the run. You have to look for the cleanliness and location of debris, where the debris accumulated during the run, and take note of that. Check for the wear and tear of the tool, ensuring that all parts are still intact and moving appropriately. Photographs are very important in this stage um, to document the tool at the receiver trap. Some examples of post-run function checks are appropriate operations of all components, the acceptability and availability of power supply in the tool. You have to confirm that all sensors are operational, confirm acceptability and availability of data storage, and confirm that all components in the inspection tool are that the tool is in recording mode. This is key. After the post-run checks comes the good part, the good stage, the data quality check, because after all, that's the reason you are in all this trouble. So check for the quality of the data. So a field or initial data quality check must be a comprehensive data quality assessment with a rapid scrolling through the data using the vendor's visualization software to detect any possible areas with missing data or with striking signals to confirm that the data meet basic quality requirements. A report with a series of specialized checks to ensure that the data has quality and integrity must contain as a minimum three things. First, the data needs to be complete. The amount of collected data must be checked after the initial processing and compare the data with the actual length of the inspected pipeline. In general, an inline inspection survey must not have data loss in more than 3% of the total coverage area. If the data show two or more consecutive failed sensors along the line, it must be evaluated with caution on a case-by-case basis, depending on the tool technology and target anomalies for inspection. The second thing that you need to look is for data plausibility. Plausibility measures how reasonable the data appears to be and the likelihood that the data corresponds to the actual conditions of the pipe. Scrolling of the data to identify the presence of known pipeline features, such as girth wells, wall thickness changes, fittings, valves, teeth, etc. This will help you to assess the validity of the data. And finally, the actual quality of the data. The degree to which the data meets the analysis requirements. It is good, excellent, degraded. Within 5 days of the run, the inline inspection vendor must provide a detailed report with the results of the evaluation. You shouldn't have to wait more than 5 days to get a report that says you have a failed run. That shouldn't happen. Okay, you need to identify any data shortfalls and issues with the data that will prevent the vendor from meeting the performance specifications. In general, the data quality checks are composed of two basic elements: the auxiliary data, and the technology-specific data. The auxiliary data may include information regarding tool speed, product, or inspection medium, temperature, operating pressure, odometer counts. And technology-specific data include, for instance, magnetization levels for magnetic flux leakage tools, and coupling loss or echo loss for ultrasonic tools. The auxiliary data helps you to determine if the tool operated within the tool specifications for speed, for temperature, for pressure. If odometer counts progresses as predictable intervals, temperature, pressure, speed, etc. This information is used in context to make general judgments about the basic operation of the ILI tool. For instance, an MFL tool that ran about the maximum speed not only will produce data with a lower axial resolution, but the accuracy of each individual reading will be totally affected by this. So you may considered a fail run for the purpose of detecting the target anomalies. Okay, now the preliminary report gets. Usually takes about 15 to 30 days after the tool comes out of the line. In this stage, you need to a checklist to based on the proper input parameters, such as the pipeline diameter is correct. The pipeline diameter in the report, is the wall thickness correct? Is the predominant wall thickness correct? The grade, the full length of the line. This is really critical. The length of the actual pipeline must correspond to the length of the inspection. For gas pipelines, at least the vendor needs to report dents, wrinkles, buckles, and ripples with metal loss regardless of orientation. If no anomalies met the preliminary report criteria, a prelim report is still required, stating that no anomalies met these conditions. But as a minimum, a list of detected girth walls, what is known as pipe book or pipe tally with AGM location must be provided. After the preliminary report comes the final report. Usually takes between 1 and 3 months. Shouldn't take more than 3 months for any technology. And after the tool comes out of the line, it's time to check again some basic information, like a pipe diameter, nominal wall thickness, pipe grade, length and total odometer counts, and the AGM list, etc. Finally, before completing the final report, you need to make sure that the analysis has the data analysis has a quality in its process. Some examples of checks are to go through the data and check for extremely short, and extremely long or unusual joint lengths. Verify in the data that the length of these joints is what you are expecting to have in your pipeline. If the tool identifies longitudinal seam wall orientations, you have to check the pipe joints with no long seam orientation or with long seams that are weird for your conditions. Verify in the data the actual wall thickness measured by the inline inspection tool, and make sure that correspond to your predominant wall thickness. Verify that the girth walls ID numbers were transferred from any previous surveys so that you can continue with the same ID numbers. Some data analysis issues may affect only specific locations, but in many cases, reanalysis of the data or an independent revision of the analysis may be needed to address some concerns that maybe are not just located in one area, but are probably common through the whole pipeline length. After making sure that you have an analysis of quality, you have to go to the data validation. Validation is the assurance that a service meets your needs. Up to this point, we have done verification to make sure that they correspond to the procedure. But now, let's see if the results meet your needs. Are the inline inspection system results consistent with the performance specification? An important part of closing the loop is the feedback from the field to the ILI provider, and to explain inconsistencies in the analysis or inconsistencies in the results. Inline inspection accuracy is typically given in terms of tolerance and confidence level, called also certainty by ILI vendors. So a simple method will be to calculate the standard deviation for this particular set of data and compare the standard deviation with the standard deviation corresponding to the ILI performance specification, which in this case, due to the confidence level And the tolerance of the tool, the 10%, plus minus 10%, and the confidence of 80% is 7.8%. So you will calculate the standard deviation for your sample. Operators sometimes incorrectly consider the overcall anomalies to be within the reported accuracy. All these anomalies that we have that are in the overcall for depth needs to be considered for the calculations of the accuracy of the tool. Adding the overcall anomalies outside of the tool accuracy will skew the data. It is also important to remember that even overcall anomalies in one category, such as depth, like in this case, this feature here, will correspond to an anomaly that was undercall for other category. Like in this case, was really undercall, about 4 inches in length. So it is important to look at it in context, all the data. This will have terrible consequences for the pressure-based assessment. As our nation's pipeline infrastructure gets older, the need for more and more inline inspection tools and analysis continues to rise. The ILI vendors, in an effort to meet the rising needs, continues their drive for greater productivity and faster cycle times. But as often happens in rapid industrial progress, a big advance in one direction sometimes results in a bigger setback in another. The reduction in cycle time of analysis sometimes brings lower quality in the analysis. This is the reason you must follow a checklist and procedures to make sure that there are no errors in the analysis or in the process of the inline inspection, and that you have a consistent quality data. This systematic approach provides the big picture of the inline inspection run. This is a means of assessing all the parameters taken as a whole to determine if the tool performance was acceptable. This parameter is a mechanism to ensure that pending or conditional items do not result in an acceptable run. Do you take the time to look for inconsistencies in the report, in the ILI data that you receive? Do you take the time to look at the inline inspection data? The time invested in reviewing the inline inspection data in context and do this checklist will bring you many benefits. After all, your top priority must be a safe pipeline operation. And this one in turn will minimize costs and maximize your productivity. Because after all, managing the integrity of a pipe is based not only on how confident, it's not really about what you found and responded using the inline inspection results. At the end of the day, the true integrity of the pipe is based on how confident you are about the features that remain in the pipe that you have decided not to respond to. Doing all of this will not guarantee that you will discover and avoid all possible preventable surprises. But not doing this correctly will increase your chances to get in trouble, to be out of compliance. Remember, your ILI data might be trying to tell you something, but only if you take the time to look. Each pipeline system is unique and may contain a variety of threats related to operating conditions, pipeline vintage, and environment. If you have any questions or need more information, please call us or send us an email. We'd love to hear from you. Thank you.
All right, thank you, Bernardo. So at this time, we have a couple questions. And if you guys have any more questions, go ahead and send them in because he's got 20 minutes if you want to fill his time. So number one question, let's see. Does API 1163 require vendors determine acceptance criteria for ILI? It says operators would then review that criteria and discuss any concerns.
There are some examples in the appendix of 1163.
Oh, okay. Sorry.
There are some examples in the appendix of 1163. There are no clear guidelines about you should accept a run if you have less than, for instance, 3% coverage loss. But what is clear is that if you accept a conditional item, for instance, you have
Muted.
lost 2 sensors in a run, you need to cover the possible consequences of missing the data. So you need to probably look for inline for a hydrostatic test pressure or look for previous inline inspection runs in order to resolve this condition that is below acceptance criteria. So if you have problems with overspeed, you will have to check those areas on a case-by-case scenario, and maybe you will need to support the acceptance of the run based on that you have a previous survey and you don't have anything in that area, and you are not expecting any changes there, or that you have a previous survey plus a hydrostatic pressure test, or conditions like that. But there is no clear guidelines as to what you should or not accept. Will be up to you to take into account all what you know about your pipeline system and your threats and the conditions of the operation of your pipe.
Unmuted. Muted.
One more. It says on the final report
Unmuted.
Specify exactly what pipe data comes only from the ILI run. Sometimes I see the source data on Rosen ILI pipe tallies that may be different than the GIS. I'm not sure which is correct.
Say that again?
It says on the final report, is there a way to specify exactly what pipe data comes only from the ILI run?
Well, when you receive the inline inspection report,
Muted.
hopefully you have established guidelines with them about the information and the way the information is presented. So probably you have given them a special template so that they can introduce the information from the inline inspection run. You can create another report when you combine data. For instance, you can ask the ILI vendor to include difference with previous inline inspection reports if they have performed a previous inline inspection. So probably you want them to put that information or to explain any differences in count of anomalies or in count of average depth. But hopefully you will have established the guidelines for the reporting in the way that when you get the report from the inline vendor, you know what comes from only from the actual inline inspection and not another ancillary data that was used in the report. Maybe if you are sending, when you mention the GIS data, probably you have already INS data, inertial navigation data. You have coordinates for each girth well, and probably you want the new report, the new vendor, to include that information. But that is something that you have to decide and talk with your ILI vendor and request them to present the data in the format that you want so that you know what exactly comes from the inline inspection and what data have been given to the ILI vendor to be included in the report.
Unmuted.
Okay. It says, how many results do you need within tool tolerance versus samples taken in order to validate tool performance? How many results do you need within tool tolerance versus samples taken in order to validate tool performance?
So hopefully you will calculate the new confidence level. So the for an ILI tool to be effective, it has to be accurate and it has to be reliable. To be accurate means to be able to size all defects within specs. To be reliable to me means to be able to size all defects. So when the vendor gives you an accuracy, it will give you a tolerance and it will give you a confidence level. The tolerance will be plus minus 10%, and the confidence level, they will call it probably the certainty, and they will give you a value of, say, 80% of the time. That means the 80% of the time the tool needs to be within the tolerance of the tool. So if you have your sample, you take, let's say that you have the total number of defects in this case is very short. Let's say that is 20. You get all these 20 features, and you will calculate the actual standard deviation of those values with the field verifications, including the error in both. And you will have a new value for the confidence level. And probably if you get 77%, like in the example that we show, that 77% is less than the 80% that the ILI vendor is giving you. So in this case, the tool didn't behave for that sample that you took. It didn't behave within the stated performance. So you will have the option to discuss the results with the ILI vendor to explain why the discrepancies. Let me show you the. Let me show you the. Like in this case, 77 is for these results. There are all these data outside of the performance evaluation. So 77% is the confidence interval, the confidence level that you have for the, instead of the 80%. You will calculate also, let me go here. You will have to look at the results that you have received, that you have calculated. You have to calculate the systematic bias error, so how the data is skewed, like in this case, is skewed on this side, and you will find the estimated random component that is the standard deviation. So those are the things that you will need to look, but you will calculate, and in this case, it's 77 less than 80%. You will have the option to accept the data if you have probably ways to get more field verifications. But to this point, you know for sure that the tool is not within the tolerance and within the confidence level stated in the performance evaluation. So it's up to you to receive the data, to accept the data. But in any case, you must contact the vendor and request an explanation for the lack of consistency or the lack of accuracy in the data. And unfortunately, this is the part where we fail to get good answers and good explanations for these reduction in the specs. You buy something and you are not receiving what you bought.
Let's see, it says, for river crossings, is there a recommended way to validate the tool if the only calls are in the middle of the river, such as above measurements, maybe?
Well, this is the problem when we rely only on one inline inspection, and usually these errors are in the worst place, in the more difficult place to verify, or are in the most terrible place if you have a leak. So the idea is that you in general, you shouldn't rely on only in one inline inspection, but probably this is not the case, and you need to evaluate the quality of the data to make sure that what was called in this river crossing is actual, is an actual indication, is a valid indication, and that only can be resolved looking at the data in context, looking at all the inline inspection, not only on the river, but the whole inline inspection. So a revision of the data probably will be needed in order to decide, okay, I have a real problem or I have a false positive. So you need to 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 verify that the tool first is working within the tolerance specified and within the confidence level, and also that that you don't have a high number of false positives within the data. So you have to study the data and to calculate these parameters, and then look at your section. You at this crossing on the river, but it has to be looking at as an individual case, but after looking at the all data from your pipeline to make sure that you are getting good data, consistent data, and that the data is dependable.
Okie dokie. Let's see. We got one more. Let me try. Okay. Is there any consideration that needs to be incorporated for error in ditch field measurements of anomalies, such as using ultrasonics when comparing the data to ILI?
Yes, depending on what you use in the field. If you use an old thorn pocket scale, of course there will be an errors, but depending on the type of survey that you are doing in the field. In general, in the examples of the API 1163, they use 5% in the field, plus minus 5% for one example. But this is something that it has to be calculated for your particular method that you are using in the field. If you are using a laser scanner, will be different than if you are using a Thorpe scale. But one problem, and is the quality of the inspector, the quality of the work of the inspector. I think we haven't improved much in to have a standard process to evaluate the people that work in the field to make sure that we have a consistent result. And this is more important for the assessment and measurement of cracks than for meta loss, but it has to be that you have a clear records of performance of the personnel that you use in the field. In the same way that with the analysis, these tools, inline inspection tools, have improved enormously in the last 40 years, but the analysis basically stays the same, but now with the increase in the speed, there is a reduction in the quality. And it stands to reason that probably the same that happens in the field. There are more pressure to get the results quickly in the field, and we don't have the quality in these verifications. But in general, depending on the method that you use in the field, you need to quantify that one. And there are very good examples for to use the API 1163 and to use both the standard, the error in the measurement in the field, and the error in the inline inspection tool. But in general, the results that we have are gross errors. For instance, in the measurement of this example, and this is from a real case, this is in a refinery, you have a difference in the inline inspection from 10 inches, the actual value, to 6 inches. So it's a difference of 4 inches. So there are errors that are way beyond the error in the field. And some vendors will explain this like, oh, but what is the standard error in the error of the measurement in the field? But it's just that the inline inspection missed completely the location of the deepest point. So we're talking about a 60 feature, 60% depth anomaly was reported 20%. So this is way independent of any error in the field. So, but yeah, there is an error that you need to calculate it and use depending of the type of and method of verification in the field.
Okay, let's see. It says, can the ILI performance be validated using different technology, such as MFL ILI validated using UT or using other technology, as some vendors have recently brought to the market that is not considered traditional ILI?
Yes, the inline inspection should be compared to previous inline inspection, no matter the technology. In fact, this happens a lot. Like you can, in general, you expect that ultrasonic tools have more accuracy than MFL tools, but in some cases, and due to the problems in the analysis and the quality of the analysis, when you compare to a previous MFL run, you will discover, especially with pitting corrosion, better results with MFL tools. So yes, you have to compare it with not only with any other previous survey or with dig verifications, but also with known features in your pipeline. And more operators are using in situ joints with machine-made defects, and this will make your life easier when you will be able to compare immediately results from the inline inspection. But yeah, don't take the results of the inline inspection at face value. You have to compare with anything at your disposal, previous other technology, and in fact, that's what the regulations says. The spirit of the regulations is that one, that you look at all the sources of information and you combine them and you look at the whole picture. That's the best approach. Compare those results and look for inconsistencies. That probably is the most important point. Look for inconsistencies, talk with your inline inspection vendor, and demand good answers for those inconsistencies. And do not proceed until you have clearly established the sources of the errors.
All right, thanks, Bernardo. We do have a couple more questions on here, but for the sake of time, I'm going to wrap up right here, and then I'll have Bernardo follow up with, if your question didn't get answered today, he'll follow up with you directly. So, and then if you think of any questions after we hang up today, you can go ahead and email him directly, or you can email me, and we'll get you in touch with the right person. So, that's all the time we have for today. We hope you enjoyed the presentation. As always, I'll send a copy of the presentation along with the link to the recording, so go ahead and keep an eye out for that. And we will see you next time. Thanks for joining.